The table below shows a list of numbers. For every number listed in the table, multiply it by 2 and then add 1. Record the result on the right. Go ahead, pause the video, take a moment to double the number and add 1 to each number on the left, and then we'll go over them and talk about some things that we might see. So the first few I did for us wrote out the expanded form of them. So each one is multiplied by 2, and then to that result we add 1. And you'll notice that we end up with 1, 3, 5, 7, 9, 11, 21, 47, 115, 201, and 619. What are some things that you might notice about the numbers in the table? Well, one student noticed that all the numbers are odd. I also noticed that all the numbers were a difference of 2 between each one. But does an even number multiplied by 2 result in an even or odd number? Well, if we have an even number and we multiply it by 2, the result will always be an even number, because multiplying by 2 doubles the number of objects we have. So as a result, all of our objects started with a partner, and now we'll continue to have a partner when we just double the amount that we have. Does an odd number multiplied by 2 result in an even or an odd number? Well, when we start with an odd number, it will also result in an even number. Because we start with an odd number of objects, not everybody has a partner. But as soon as we double the amount that we have, soon that last piece that did not have a partner will now have a partner, and everyone will have a match, therefore giving us an even number. Does an even number plus 1 result in an even or an odd number? Well, an even number plus 1 will always be odd. Because there are an even number of objects, each piece will have a partner. However, if we add one more of those objects, there's going to be one left over that won't have a partner. Does an odd number plus 1 result in an even or an odd number? Well, an odd number plus 1 will always be even. If we start with an odd number of objects and there's one left over without a partner, if we add one more piece in, then that odd one will automatically now have a partner to pair up with, so every object will then be paired up. So going back to our original part, explain why all the numbers we entered in the table were odd. Well, we can use some of the understanding that we had from the previous questions to conclude that the values in the right column are all odd because we first multiplied either an odd or an even number by 2, and we just discussed that no matter if we start with an odd or an even, when we multiply by 2, the result is always an even number. But then we're adding 1, and we decided that an even number added 1 to it will always be odd. We further can write the generic form of that pattern. No matter which number we choose, n, we'll just call it the generic n. The pattern we did was take 2 times whatever number that was in the sequence and then added 1 to it. Moving on to operations in base 10, there's a lot of things happening here. We're still going to add, subtract, multiply, and divide. We're going to take it a step further than we did in 3rd grade. So let's start with an input and an output table. I want to know, how do we get from the input to the output? What is the operation that we're doing? So they have an example there for us. So how do I go from 6 to 60? Well, it looks like we multiply by 10. So I can fill in the chart. 12 times 10 is 120, 25 times 10 is 250, and then I ask what times 10 is 320 and what times 10 is 470. So we can fill in the chart. Let's take this chart one step further and repeat the result. So 2 times 10 is 20, 20 times 10 is also 200. So I can finish filling out my chart as 1200, 2500, 3200, and 4700. I see that by multiplying by 10, we are shifting our digits. We also know that the value of a digit depends on its place value. But what happens if we shift to the left? So I see that going from 12 to 120, I'm shifting my pieces to the left. So my tens goes to the hundreds, my ones goes to the tens, and then I use 0 as a placeholder. So 110 times 10 gives me 100. 10 times 10 is 100, and 2 ones times 10 is 2 tens. So 2 times 10 is 20. Further, if I shift it left and then left again, so notice that we go to the thousands, the hundreds, the tens, and we keep going and adding a 0 for a placeholder. How does the value of the digit in the tens place change when the number 53 is shifted to the left? Support your thinking using an equation. Pause the video, take a moment to try to see if you can write this out yourself, and then we'll talk about it. So I know that 50, when I decompose 53 into 50 and 3, they're multiplied by 10. Each part, so 50 times 10 plus 30 times 10 gives me 500 plus 30, so 530. Notice when it's shifted to the left, 53 becomes 530 when I take 53 times 10. Let's say we have the following representations of numbers. How can we sort these representations? So I see I have an assorted ways that I can write a bunch of different numbers. I'd like you to fill out the table using standard form, word form, expanded form, and base 10 representations. Pause the video, sort these out, and then we'll talk about them. So written in standard form, we should have 421 and 214. The word form, expanded form, and base 10 pieces. This may not have been the original way when presented this problem you would have sorted. Rather, my first inclination is to sort them out based on which number they represent. So writing 421 using numbers, expanded form, and the written word, 223 using the standard form, written form, and base 10 pieces. But it doesn't matter the way we represent using the different forms. Changing how it is written does not change its value. Equivalent numbers have the same value no matter how they are written or represented, just as we saw in the previous slides. Pause the video and fill in the missing information, written in numeral form, expanded form, and base 10 blocks. Part A, we should get 2067. Part B, we should get 800 plus 40 plus 3. Part C, we need a flat and a long, or a 1 100 piece and 1 tens piece. A friend asks you to check their homework to decide if the answers were correct or not. Thinking about when rounding to the nearest 10, what is the smallest whole number that will round to 100? Your friend answered 90. What is the largest whole number that will round to 100? Your friend chose 104. How many different whole numbers will round to 100? Your friend chose 5. Stop the video, determine if A, B, or C are true or false. Part A is incorrect. The whole numbers which would round to 100 would include 95, 96, 97, 98, 99, 100, 101, 102, 103, and 104. Those are all the numbers that would round to 100 when rounding to the nearest 10. Therefore, the smallest is 95. Part B is correct. Looking at the numbers listed above, the largest is 104. Letter C is incorrect. Looking at the list above, we see there are 10 possibilities, not just 5. During a competition, you can jump rope 234 times. Your 5 teammates also jumped rope about the same amount. Estimate how many total times your team jumped rope. We're going to use estimation. So I'm going to look at 234 and I'm going to round to the nearest 100. I see that 200 is closest to 234 when rounding to the nearest 100. I'm going to take 6 and round it to 10. So I could estimate this as 200 times 10, which is 2,000. I could also take this as 200 times 6 itself, since that is easy enough to multiply for that 1,200. Similarly, I could take 234 and multiply by 10 and get 2,340. Again, these are all estimations depending upon how you're rounding. Let's round to the nearest tens. Let's say I round 234 to the nearest 10, which would be 230. I could then round 6 to the nearest tens, which would be 10 itself, for 2,300. It's very interesting to see that depending upon how we round depends upon the estimation that we find. Rollo has 159 pennies and Zeus has 1,431 pennies for a fundraiser. Zeus is excited to share about how many times more pennies he has compared to Rollo. Zeus says, "I collected 10 times more pennies than you." Rollo says, "No, only 5 times more." Explain the estimation strategy that Zeus and Rollo each used and argue which way makes the most sense mathematically. Let's take a look at Rollo's estimation. It looks like Rollo rounded to the nearest 100, so 159 would round to 200, and 1,431 would round to 1,000. 200 times what would give us 1,000? So 200 times 5 is about 1,000. That's how Rollo got the 5 times more. Let's look at Zeus's estimation. Zeus estimated that 159 is closest to 150 when rounding to the nearest 10. He also rounded 1,431 to the nearest 100 as well for 1,500. So he asked 150 times what gives us 1,500. Easy enough to mental calculate that 150 times 10 is 1,500. Again, Rollo and Zeus rounded differently, so the number of times they get is also different. Not necessarily wrong, but just different. Let's use a tape diagram to find the exact answer. Zeus's pennies were 1,431. Rollo's were 159. I need to know how many orange can fit onto the blue bar. I see that 159 will fit on the blue bar 9 times. So 159 pennies times 9 is 1,431 pennies. So when I put their estimations next to each other, although both strategies are correct, Zeus's strategy on the right here of rounding to smaller place value makes more sense mathematically because his estimation is closer to the actual answer. Number lines are an effective tool when rounding numbers to any place value amount. Recording benchmark numbers based on place value on number lines helps show which numbers are closer to one another. We know that deciding which place value to round to is an important part of estimation.